Our goal in this tutorial is to give you a broad understanding of how transistors work. Also, we will not go into the deep details of semiconductor basics or equivalent models. But we will go into transistor operation enough to understand how a transistor can be used as a switch or amplifier.
Transistors surround the world of electronics. The presence of these electronic components is used in almost every modern circuit as a critical control component. Sometimes these parts can be seen on electronic boards, but today they are often used in an integrated circuit, IC, and are hidden from our eyes. In this educational video, we explain the most common transistor, the bipolar junction transistor, BJT, and other transistors. The transistor is the most important part in electronics and is used as a switch to amplify or cut off signals. Transistor is one of the solid-state devices made of semiconductor materials such as silicon and germanium. A transistor has N and P-type junctions in its structure. I in the topic of diodes, you learned how to make semiconductors and connect P and N. Therefore, we refrain from repeating those contents in this video.
Types of transistors. Transistors are generally divided into two categories, the bipolar junction BJT and the field effect FET.
Bipolar junction transistor, BJT. Bipolar junction transistors are turned on by an input current applied to the base. BJTs have low input impedance. According to the type of connection and the placement of these bases, they are made in two types, PNP and NPN. PNP is a type of transistor in which an N semiconductor base is placed between two P semiconductor bases. Also, when a P semiconductor base is placed between two N semiconductor bases, an NPN transistor is made. NPN type is one of the most widely used transistors.
NPN and PNP transistor symbol.
Transistors basically have three bases. In BJT, these bases are called collector, base and emitter, and we show them with three letters B, C, and E respectively.
Structure of transistors.
Transistors are made by placing three different layers of semiconductor material together. Some of these layers have had extra electrons added to them, a process called doping, and others have had their electrons removed. In fact, these substances are contaminated with holes, absence of electrons. A semiconductor material with an extra electron is called an N-type semiconductor, and a material from which the electron has been removed is called a P-type semiconductor. The letter N at the beginning of the word means negative and is used because of the negative charge of the electron. The reason for using P is that the charge is positive due to the presence of holes. Transistors are made by placing N semiconductor material on both sides of P semiconductor or vice versa. The NPN transistor is designed to pass electrons from the emitter to the collector, so the usual direction of current is from the collector to the emitter. The emitter emits electrons to the base. The base controls the number of electrons emitted. Most of the emitted electrons are collected by the collector and then circulate in the circuit. A PNP transistor works in a similar way, but in reverse. In this transistor, the base still controls the current, but the current is in the opposite direction, from the emitter to the collector. This time, instead of electrons, the emitter emits holes that are collected by the collector. A transistor is kind of like an electron valve. The base is like a valve that you can adjust so that more or less electrons flow from the emitter to the collector. We will examine this and now. There are three modes in the circuit that we can use as the example of a faucet, and each one has a different effect on the amount of current in the circuit. 1. Open water valve. 2. closed water valve. 3. Adjusted water valve. In the following, we will examine these modes. 1. Short circuit, connected transistor. Like an open water valve. 2. Open circuit, disconnected transistor. Like a closed valve. 3. Making the flow linear. Like when we put the faucet between closed and open as desired. 4. Amplification. Imagine being able to control the flow of the valves of a large dam with a slight turn of the valve. The very small force you use to turn the valve has the ability to create thousands of times more force. Transistors can amplify electrical signals and convert a low-power signal into a similar signal with much higher power.
Transistor working areas.
Unlike resistors, whose relationship between voltage and current is linear, transistors are non-linear devices. In fact, transistors have 4 distinct states or regions of operation that describe the current through them. Again, we emphasize that when we talk about current through a transistor, we usually mean the current from the collector to the emitter of an NPN transistor.
Field effect transistor, FET.
Field effect transistor, FET. These types of transistors control and determine the shape and size of the channel based on the unipolar voltage. In fact, FET transistors perform the role of voltage control. Field effect transistors have much less energy consumption and heat loss than connected bipolar types. Also, the amount of noise and sound of these transistors and the amount of their input impedance is higher than the types of connected bipolars. 2 types of junction field effect transistor and metal oxide semiconductor field effect transistor are types of field effect transistors. Also, JFETs are divided into 2 categories, JFET N-channel and JFET P-channel. MOSFETs are classified into 2 categories, depletion mode and enhancement mode.
UJT transistor.
A single junction transistor, UJT, is a type of 3-terminal semiconductor device that can be used in timing and triggering circuit applications to control and switch triacs and thyristors used in AC power control systems. Like diodes, single-junction transistors are made of separate N-type and P-type semiconductor materials, with a PN junction, hence the name single junction, forming in the main N-type conducting channel of the component. Although the single-junction transistor has the name transistor, its switching characteristics are very different from those of bipolar junction transistors or field effect transistors. These transistors cannot be used for signal amplification, but instead can be used as switching off transistors. UJTs have unidirectional conduction and negative impedance properties that make them act more like a variable voltage divider during breakdown. According to the equivalent circuit you see, the N-type channel basically consists of 2 resistors RB1 and RB2 placed in series with an ideal diode, D, representing a PN junction and connected to the center. Resistors. This PN junction emitter is placed in a fixed position along the ohmic channel during the manufacturing process and cannot be changed. Resistor RB1 is placed between the emitter and terminal B1, while resistor RB2 is placed between the emitter and terminal B2. Since the physical position of the PN junction is closer to the B2 terminal than the B1 terminal, the resistance value of RB2 is lower than that of RB1. If a small positive input voltage, which is smaller than the RB1 resistance voltage, VBB, is applied to the emitter input terminal, the PN junction of the diode will be negatively biased, resulting in a high impedance and the part will not turn on. The UJT is off and the current is zero. But when the emitter input voltage rises and exceeds VRB1 or VBB plus 0.7 V, which is 0.7 V equal to the voltage drop across the diode's PN junction, then the PN junction is forward biased and the UJT is activated. And as a result, the emitter current IE flows from the emitter to the base region. A single junction transistor is a trigger semiconductor device that can be used in a variety of circuits and applications, from lighting triacs and thyristors to use in sawtooth generators for phase control circuits. The negative resistance characteristic of the UJT makes this part useful as a simple relaxation oscillator.
Mosfet transistor.
The Mosfet transistor is equipped with three bases, source, gate and drain. By applying voltage to the gate base, the electric current between the drain and source bases can be controlled. When you press the key in your room, the electrical circuit is connected and the electric current reaches the lamp. So the voltage applied to the gate does the same thing in the Mosfet. Connecting the gate to the voltage source causes the resistance between the drain and the source to decrease drastically and create a channel for the flow of current from the drain to the base of the source. When no voltage is applied to the gate, the drain to source resistance increases sharply and the current path is lost. Classification of Mosfet. Mosfet transistors are divided into two categories, Mosfet enhancement and Mosfet depletion. In enhancement Mosfet, no channel is created in advance between the drain and the source, and by applying the appropriate voltage to the base of the gate, the current passing channel is created. The width of the channel depends on the voltage level applied to the gate, and as a result, the current passing through it can be controlled. In the depletion type, the channel is created by the manufacturer, and by applying voltage to the gate base, we can change the width of the channel. While the enhancement Mosfet is by default without applying voltage to the gate base, the depletion Mosfet is connected due to the presence of the channel, and by applying a negative voltage to the gate base, we can reduce the width of the channel. In general, enhancement and depletion MOSFETs are made in two types, N and P, in which the current flows from the drain to the source, and in the P type, the current flows from the source to the drain. Application of Mosfet.
These types of transistors have wide applications in electronic circuits, and thanks to the advancement of technology today, we can put millions of MOSFETs in a memory chip or microprocessor. In addition, it is common to use this transistor as a voltage-controlled switch in electrical circuits. The Mosfet transistor is so important that without it, it would not be possible to make a pocket calculator and wristwatch. These transistors are used in making IC integrated circuits, CMOS circuits, analog switches, power electronics, MOS memory, sensors and quantum physics.
Insulated gate bipolar transistor, or IGBT for short, is a semiconductor device that has a function between a bipolar junction transistor, BJT, and a field effect transistor, Mosfet. The IGBT transistor has the best parts of the two common BJT and Mosfet transistors in its structure. In fact, the large input impedance and high switching speed of the Mosfet and the low saturation voltage of the BJT combine to create another type of transistor, the IGBT, which is capable of operating at high values of collector-emitter current, with almost zero gate voltage. As the name suggests, IGBT is equipped with isolated gate Mosfet technology and also has a common bipolar transistor. The result of such a combination has the output switching and conduction characteristics of a bipolar transistor, but is a voltage-controlled device like the Mosfet. IGBTs are widely used in power electronics applications such as inverters, converters, and power supplies that require switching components where Mosfets and BJTs do not perform well. High voltage and high current bipolar transistors are available, but their switching speed is low. On the other hand, although the switching speed of power Mosfets is higher, the high voltage and high current components are expensive. IGBT structure. Insulated gate bipolar transistor has more power than standard bipolar transistor. It also has the ability to work at higher voltage and lower input losses. From a functional point of view, the IGBT is a FET combined with a bipolar transistor to form a Darlington configuration. The IGBT is a 3-pin conduction device that is made by combining an N-channel Mosfet with an isolated gate at the input and a PNP bipolar transistor at the output, forming a Darlington circuit. Therefore, the bases of IGBT are called collector, emitter, and gate. Two of these bases, C and E, correspond to the conduction path through which the current passes. The third pin, G, also controls the segment. The value of the IGBT gain is equal to the ratio of the output signal to the input signal. For a typical BJT, the value of gain is approximately equal to the ratio of output current to input current, called beta. In a Mosfet, the input current is zero because the gate is isolated from the main channel current. Therefore, the gain of the FET is equal to the ratio of the change in output current to the change in input voltage, which leads to this semiconductor being a conducting device, as is the case with the IGBT. Consequently, we can consider the IGBT as a power BJT whose base current is fed by a Mosfet. IGBT transistor can be used like BJT or Mosfet in small signal amplifier circuits. But since the IGBT offers the low conduction losses of the BJT with the high switching speed of the power Mosfet, it is an optimized switch that is ideal for use in power electronics applications. Also, the IGBT has a lower on-state resistance or RON than its equivalent Mosfet. This means that the power dissipation in the bipolar output is lower for a given switching current. The direct blocking function of the IGBT transistor is similar to that of the power Mosfet. When we use the IGBT as a static control switch, this part has the same voltage and current values as the bipolar transistor. Of course, the isolated gate in IGBT needs less power than BJT. An IGBT can be turned on or off simply by enabling or disabling the gate pin. Similar to most MOSFETs and BJTs, the IGBT is turned on by applying a positive input voltage signal to both the gate and emitter terminals. While the gate signal becomes 0 or slightly negative, the IGBT turns off. Another advantage of the IGBT is that the channel resistance in conduction mode is lower than that of the standard Mosfet. Since the IGBT is a voltage-controlled device, it requires only a small amount of gate voltage to remain in conduction. Unlike BJT, which needs constant supply of base current to stay in saturation state. Also, unlike the bidirectional Mosfet, the IGBT is a unidirectional device, i.e., it only transfers current in the direct direction from the collector to the emitter. MOSFETs have the ability to pass controlled current in the direct direction and uncontrolled current in the reverse direction. The operating principles of trigger gate circuits in IGBTs are very similar to N-channel power MOSFETs. The only major difference is that when current flows through the IGBT in the ON state, the resistance of the main conduction channel is much lower than that of the Mosfet. Conclusion.
In conclusion, it can be said that the main advantage of using IGBT over other transistors is the ability to work at high voltage, low on-state resistance, simple setup, relatively high switching speed, and zero gate startup, which makes them a good choice. For high voltage applications such as modulation, pulse width, PWM, variable speed control, switching power supplies, or solar DC-AC inverters, and frequency converter applications in the several thousand kHz range. To be
Transistors based on performance.
Small switching transistors are used for switching and sometimes in amplification. The amplification performance of these transistors is not very strong, but they perform better in the switch. These types of transistors are available in NPN and PNP models. The current required for it is 10 to 1000 milliamperes.
Power transistors.
Transistors used in high-power amplifiers and power supplies are called power transistors. There are transistors of this type in the form of NPN, PNP, and Darlington transistors. Their collector current is between 1 and 100 amperes.
High-frequency transistors.
RF transistors are used in high-speed switching applications, as well as for small signals operating at high frequency. RF transistors must be turned on and off at high speed. NPN and PNP types of high-frequency transistors are available in the market. These transistors have a current between 10 and 600 milliamps. High-frequency transistors are used in oscillator and amplifier circuits such as CATV, UHF, VHF, MATV, and HF.
Application of transistors. Due to their different characteristics, transistors have found many and varied applications in components and circuits. Transistors are used as switching, power supply, voltage regulator and amplifier, oscillator, and IC. These parts are used in analog and digital electronic circuits. In digital circuits, transistors are used in making various parts such as switches, logic circuits, memory such as computer memory, etc. In these circuits, transistors have the role of turning on and off the current. In analog circuits, transistors play the role of amplifying electric current. FET transistors are used to reduce the loading effect, i.e. in voltmeters, phase shift oscillators, etc.